Okay, let's start our meeting for tonight. So this is our second night for the one-week international webinar on science in the 21st century. So I welcome everyone who's attending the webinar tonight. So tonight our resource person will be Professor Thapa, who is a retired professor from Department of Physics, and he is my supervisor itself when I was doing my PhD. Myself is Dr. Rebecca Leomi, Assistant Professor of Department of Physics, Government Retd College. So before we introduce our resource person, I will give a few description about his biodata, his credential, and also I shall be sharing my screen. Please bear with me for a minute. I hope you can see my screen from your side. So let me give a brief introduction about our resource person for tonight. So as I have said, he is Professor Thapa, who is a retired professor from the Department of Physics, Mizoram University, and he did his BSc from St. Anthony's College, and he completed his MSc from Guwahati University in 1977, and a PhD from North Bengal University, Darjeeling, in the year 1994. So he has many years in teaching and research. In teaching, he has 40 years experience both in MSc and BSc. Earlier, he used to work in PUC, Pachung University College, and when in Mizoram University was established, he was the founder, head of the Department of Physics, which was established in the year 2005. So he was the head of Department of Physics till 2010, and thereafter he was also a dean in the department in the School of Physical Science, and also he has numerous positions such as proctor, EC, and court member under the under Mizoram University. So under his guidance, he has produced 21 PhD scholars, and he examined more than 50 PhD theses as well as MPhil dissertation, and he has a number of research projects under various projects. So he has got 9 research projects and has already published 3 books. And in addition to this, he has also published more than 150 research paper in peer research review under peer research review, and he has also collaborative researcher with various institutes in India and abroad. He has also visited many foreign like UK, Germany, in which he has collaborative research with various laboratory and institute as well. So he has also received various awards and honors, such as Best Science Teacher Award under Mizoram Legislative Assembly as in the year 1986. And so as I have shown here, so he is also Eminent Physicist Award in the year 2012 itself. So awards such as Director in the Condensed Matter Physics Research Center, Budwal, Nepal itself. So in addition to this, he has also He has also received many honoraries as well. So we are fortunate to have him tonight. So I will invite him. So, sir, tonight we are fortunate to have you as a resource person. So, sir will be carrying on with his. Sorry, there is some internet problem with, from my side. So, sir, the time is yours. I'm handing out the time.
Okay. Thank you, Dr. Rebecca. Thank you very much for giving very nice introductions. But just then I would like to make two corrections. One is number of publications is more than 250. Okay. More than 250. So that is one correction I would like to make. And first of all, I would like to thank Dr. Rebecca Lalgayomi, who was my direct student from BSc onwards to PhD. I'm very much fortunate tonight, this evening, to have her as my host. Thank you very much. Respected principal of Government Censorship College, the esteemed teaching staff, and the students. It's my great privilege this evening to give this talk on this occasion of webinar on 21st century in science, achievements in science, let us say. So I'm very much fortunate to have been invited to give this talk. I had been very much associated with Censorship College, Government Censorship College. I remember those days when I went there as a chairman of the inspection team, and when I was the dean, then I had interaction with the principal, the then principal, and the staff and all. It's a beautiful place. And again, I went second time also, stayed there overnight. I really enjoyed the stay, the hospitality I still remember. I really thank you. And once again, I thank the organizing committee for giving me this opportunity to give a talk on this webinar. Anyway, the talk, as I was informed by Dr. Rebecca, was achievement of science in 21st century. Now, there are a lot of things about science which we cannot discuss or talk in this short time webinar, rather my PPT presentations. In fact, I was informed a little late, that's why I could not make very nice presentation also. So I have to go for a technical type of presentations. In fact, it was a very nice title of this webinar. However, I will try to give talk on this field emission study, sorry, with which I had been associated, and also with this emission of electrons from solids. Dr. Rebecca also had been associated because she has done her PhD under me on photo emissions and on energy band structures few solids. So today the title of my talk will be Theoretical Study of Surface Effect in Photo-Assisted Field Emissions, which is also called photo field emission. Photo means light in physics. Photon means light, which has got energy as according to quantum theory of light. So this light is interacting with the solids. When we talk about solids in physics, it always means a metal, means the ultimate constituent parts of metal or solid is nothing else but atoms, then subparticles are electrons and others are there. So it is the interaction of rather electrons with light. Photon means light. So this produces photo field emission phenomenon. So this is the talk today I'll be giving. So before we start with our talk, with this technical talk, I would like to say a few things about this greatest scientific achievements in 21st century. A few of these I've highlighted. Now, many of you are already familiar with this one. So this I've just taken from Google, and this is truly fact also. The first rejection of gravitational waves. We know in 1905 or a little later, Professor Albert Einstein has propounded two theories. One is general theory of relativity, another one is theory of gravitations. Now it is being proved his theories were not understood by the scientists, physicists of those years, of those yesteryears. So that's why now his theory, whatever he has propounded, had been experimental proof. So recently, now the gravitational waves, that was because of LIGA project in the USA. They could detect the gravitational waves and they have measured the gravitational waves, and which has given a breakthrough in the concept of this gravitation in the universe or in nature. And on this, I would like to mention also about Professor Stephen Hawking, who was one of the greatest physicists of this century after Einstein, who died in 2018 in the month of March. So he has also given a lot of contributions on these gravitational waves. Then the evidence of waters on Mars. This is also one of the achievement of science, because if Mars has got water, means oxygen will be there. So there may be a competitions for colonizations of Mars in future. So robotic body parts, all of you understand this one, that advancement in HIV cure. This is a great medical feat that HIV can be cured now. The existence of dark matter, this is in fact Stephen Hawking, we should give contribution to him, we should remember him. The creation of human organs, the biologists, the physiologists, they are working on this. The climatology study to control it.
Sir, may I interrupt you for a minute? So are
Yes,
you, we want to share your screen. It's not been shared yet.
is it, sir? This is not visible?
Visible, it's not visible, sir.
Okay.
Your slide is not visible.
Okay, I'm just going to do it. Is it okay now?
It's coming, sir. Yes, yes.
Is it okay?
Sir, if you can.
I'm scrolling down, just check.
Yes.
Is it okay?
Yes, sir. If you can put it in the full screen mode, it will be more.
Okay.
Nice.
See now?
Okay, sir. It's fine. It's doing fine.
Is it coming?
Yes, sir.
Okay, fine. So this is the content of my talk. Sorry, just before this. So these are the latest achievement, and electric vehicles in worldwide now. Governments are spending billions of dollars to come out with electric vehicles. So this is the way the scientists are working on the production of electric vehicles. The scientists from all fields. And advancement of computers, we know very much. I myself had started the work with this desktop computer with 20 MB hard disk drive capacity. Now you know, if I say 20 MB hard disk capacity, people will laugh at me. So these are the achievements. Now we have got huge memory computers. Even the RAM of these our mobiles and also so much increased now. Mobiles, we can use it at computer now, rather like a laptop and all. Okay, these are achievements. The contents of my talk will be introduction. Then I'll be talking about a little bit of aerodynamics of surface, because this is very much involved in our study of photofield emissions. Then I will give you at the end conclusions after giving some results and all. Okay. Then the few list of publications. Now, my PPT is the presentation of Dr. Ralph Rosangliana from Jitri, Government Jitri College. So when he worked for his PhD, he has prepared this one. So I'm basing all my talk on him. So I thank him for this, really. I should acknowledge this. Application of photofield emissions. It is in photoassisted STM surface tunneling microscopy to measure direct dose, potential variance, etc. then study details of emission process, optical tunnel process, etc. Then current switching process. These are few applications. Then field emission diets, okay, displays. I'm giving you the field emission displays is that panel screen that combines LCD and CRT. LCD and CRT. CRT means cathode technology. Okay. It retains the sharp, clear, high quality image associated with CRT than this normal LCD screen TVs and all. Field emission microscope for better resolution widely used. Okay. So these are the introductions. Photoassisted field emission or photofield emission as we call it is a technique in which a metal is radiated by an incident laser radiation of photon energy S cross omega, which is usually less than the work function of the energy. Now the work function is the minimum energy required to excite an electron from a solid into the vacuum, means outside the solid, so that it will contribute to the current photofield emission current. The incident radiation photo excites the electron to a state which lies between the Fermi level and the vacuum level. Hence, these electrons are confined within the metal. So they are still not at outside the metal, because the energy of the incident radiation, which is called the photon laser radiation, is less than the work function. So it is confined within. So then in order to stream out these electrons outside into the vacuum so they will contribute to the current, means the informations, a strong static field of the order of 10 to the power 11 volt per meter has to be applied to this solid, means to the surface of the solid, so that these electrons will tunnel out to the surface potential into the vacuum and will contribute to the current, as I've said, called photofield emission current. These electrons, which are now emitted in the vacuum region, constitute the measurable photoassisted field emission current or photofield emission current, we call PFEC. The incident radiation which causes the transition of electrons from the initial state is given by I. I is the initial state, is a vector, is a mathematical representation of the state of the electron, then to the final state. And the matrix for this transition can be written as MFI, means I is initial state to final state. Transition from initial to final state is given by F A dot P plus P dot A. A is a vector potential, which is very, very important. It measures the automatic field part of the incident radiation. We know from quantum mechanics that light has got two components which are perpendicular to each other vectorially. Is called the electric part and the magnetic part. Electric part gives contribution to the current. Okay, so it is measured by this vector A as given in this equation I1, and P is your momentum operator, that is in quantum mechanics. So in my talk, I will be emphasizing on these two models. It's called free electron theory and chronic penny potential model. On the basis of this, the results are obtained for photofield emission current and are present in this talk. Okay. Now, free electron current means the electron can move about freely inside the solid. When you say freely inside the solid, there is no potential acting, no force field are there. So we call it empty potential. And the initial state wave function is deduced in the case of empty potential by simple algebraic method, matching the initial function wave function, and is derived at the surface plane defined by z equal to 0 plane. So we will calculate photofield emission current PFEC as a function of various parameters. And chronic penny model potential means we define the potential inside the solid is not empty potential, means force field is 0. It has got some value. In fact, we can define it by delta potential barrier. It means some kind of force is acting on the electron. Then we find out the current after finding out the initial wave functions. Means evaluate the transition metric element that was given by equation I1 and find by using the appropriate formula which will be shown, we will find out the photofield emission current as a function of various parameters. Chronic penny potential model seems to be something realistic than free electron model, because a solid cannot have empty potential. Always a force is acting on the moving electrons. So that force field is defined by chronic penny potential barrier. As I've said, it is defined by the delta potential barrier. And we have calculated the initial wave function and found out the photofield emission current. Okay. Now, transport Hamilton scheme, this was a part of the thesis work of Dr. Rosang Liana from Jiteri College. So I'll be omitting this one. I will not do this one. Okay. Now, the formula used for calculating the photoemission current is given by the equation 2, I2. It is given here. And the matrix element which I've defined simply in equation 1, I1, is given by equation I3 now when it is expanded. Now, I will not focus much on these algebraic things and on these quantum mechanical terms. Okay. Now here, what I would like to mention is that equation 2, I2, the main formula is taken from the paper, from the works of Professor Gao, which was published in Physical Review in 1987. Professor, here to just to mention, I acknowledge the papers, the thesis sent by Professor Gao, which was so much useful to my students, from which around 3 PhDs were produced. He's my very good friend. He's still there in USA. Then transfer Hamiltonian formula, as I've said, I'll omit this one. It's really tough. This is the survey of literature. Survey of literature goes back to Igor Tamm, Tamm Tamm, a Russian physicist who was a Nobel laureate and who has done extensive work on surface physics. And Shockley is one of the discoverer of semiconductors. Then some experimental work done by Plummer and Gazdu, 1970. Then green functions methods was used by Bakchi and Kaur. And Bakchi and Kaur, because we are using, Professor Kaur happens to be my supervisor, we're using their model for finding out the vector potential, which I'll be discussing a little bit here. And Bakchi is given a very nice detailed work in 1974 in his paper published in Physical Review. So then Lee and Reifman professor is there, who have said that there are oscillations. He did experiment and said that there are oscillations in the current, PFEC current. Okay. Then we will compare also the works of this Moses client who said that oscillations are there. And we did our work and we proved that there is no oscillation as such. Garland reference, as I said, 1987. And there are some works done by me and my previous PhD students, Dr. Das from Classic College, Government Classic College. Then there is some papers by Leszek, who happens to be my collaborator from Poland, Wrocław University. I'm very much grateful to him for inviting me 2 times there. Then let us go to chapter 2, that's electrodynamics of the surface. Chapter 2, because it is from the thesis. Now, electrodynamic surface, we have to do it we have done in a very simple way. As on a figure 2.1. We consider a surface of starting with D. Then on the left side, D is the width of the surface. On the left side is the bulk, and on the right side, Z equals 0. This is the surface plane, and on the right side is a vacuum. So there is an incident radiation of energy H cross omega, and then gets reflected, obeying the ordinary laws of reflection. We have to form a model for dielectric response function, which is very, very important for calculation of E, the vector potential, as I've said, from this electrodynamics point of view. Now, in figure 2.1, I have shown you the mathematical dielectric model, which is defined by epsilon omega Z, and it is defined for 3 regions: vacuum, surface, and bulk. Our vacuum is Z equal to 0, Z equal to greater than or equal to 0, is equal to 1. Our response function, dielectric response function E omega Z will be equal to 1. And Z equal or less than D is the bulk side, is normally epsilon omega, which is frequency dependent. Epsilon omega is the real part epsilon 1 omega plus imaginary part epsilon 2 Z. Sorry, it should be omega, not Z. I'm sorry, this is a mistake. Okay, it's a function of frequency, so it should be omega. This is for the bulk. As you all know very well from simple class 12 physics also, that the dielectric function of a solid is equal to real and imaginary part of a dielectric constant, that is epsilon 1 and epsilon 2. And in the surface region, which extends from 0 to minus D, it is simply an algebraic model, simple modeling. So it is given by 1 plus 1 minus epsilon omega Z by D. Now this is modeled out in such a way that when we put the value of Z that is equal to 0 and minus D, it gives you both the values. That is 1 and epsilon omega equal to epsilon 1 plus epsilon 2 real and imaginary parts. So this is knowledge by interpolation method. So we make use of equation 2-1 in our electrodynamics calculations and get the vector potential, or which is nothing but algebraically we can vectorally rather we can write it as an electromagnetic field. Here we see a little bit of our aerodynamic calculations. Consider P polarized light of frequency omega incident on the surface, making the angle of incidence equal to theta I. Then using various formulas and principles and all, then we find out the vector potential, out of which the equation given at 2.5 is the most important because it's a very long page calculation, almost 30 to 35 page calculations. So skipping all those, so I'm straightway going now, basing on this equation 2.5 for the long wavelength limit, okay, WD divided by C tends to 0. The value of the vector potential A omega Z means it is frequency dependent omega and spatial distance dependent is Z, is given by equation 2.6 for 3 regions. Z equal to Z greater than 0 means vacuum, Z less than minus D is the bulk, and Z between 0 and minus D is in the surface. So this has been calculated. In fact, this has been recalculated by Dr. I should say Professor B. Joliana from Government Jitgiri College when he was doing his PhD. I made him recalculate, and he has done all these recalculations and got exactly this calculation as obtained by the previous authors. So this calculation is still with me. If anyone's interested, you can always ask me. I can just share this one with you. Then in chapter 3 is the theoretical study of photofield emission by using free electron chronic Perry model. As I've already told you in introduction, I'll be these 2 models for calculating the photofield emission current. Figure 3.1 shows the model. So we have shown here for the vacuum, it is shown by the red line, which is triangular barrier, and blue one is triangular barrier in fact, and this is the image surrounded barrier. When you consider the image potential, it will be image surrounded barrier. This is the red line. Then as a function of Z is shown by this dotted line. So this is the model used for calculating the photofield emission current. Now, on the right side, we have shown the variation of the potential. On the left hand side, we can see the location of the electron in the surface and in the vacuum. Now, EF is the Fermi energy, which you all are familiar, I believe, because nowadays these are taught in +2 physics itself. And EI is the initial state energy of the electron, which is below the Fermi level EF. And when an incident laser radiation of energy S cross omega is incident, electron just goes maybe around EF, means the Fermi level energy, but it is below the vacuum, E equal to 0. So it is still loitering around here. So it is not out into the vacuum side to contribute to the photofield emission current. So we have to apply a very, very strong static field of the order of 10 to the power 11 volt per meter. Then only it will be excited in the vacuum and contribute to the current. We will have energy E current. This is the model we have. We have shown the model triangular barrier, then image potential we have shown. Okay, all these are shown here. And we find that by the application of the static field, the work function is changed. There is a small change del phi, because phi is the work function. They change, means decrease is there. That's why the electrons can be emitted out into the vacuum with kinetic energy, E kinetic. Okay. Now, this is the formula that we will be using for calculating the photofield emission current 3.1 as given by Gao and Reifenberger in Physical Review 1997. This is the matrix element expanded form. So this is this gives you the calculation of transmission probability d omega, which we have done in free electron model, and we are using this one calculated by using free electron model in the chronic Penny model as well as transfer Hamilton technique also. This is the way to calculate, and this is used back in the photo emission field formula. So here we are writing down the initial state wave function that we have deduced quantum mechanics equation 3.6 of the initial wave functions, and 3.7 gives you the final state wave functions. So these two are used. These are the initial state wave vector, final state wave vector psi f. Okay, these are used in the formula to calculate the current. Now these are the data that we have used for calculating the photofield emission. We used the width of the surface as 5.892 angstrom unit. Initial energy is given EI is 2.1488 electron volt. Potential barrier height is 15 electron volt. This is based on some paper experimental values. Work function 4.92 is standard value. That is 10.06. Okay, and we have used the live Fujitsu Fortran compiler for calculating this current by making the Fortran calculus, programming. We present here the results of photofield emission current from tungsten. As an example, we have taken tungsten and calculated photocurrent as a function of initial energy, photon energy, and so on and so forth. Okay, results are given here. I'm explaining the results here. In figure 3.2, we have plotted photofield emission current as a function of initial energy. With zero energy means it is referring to the Fermi level, Fermi energy. It's below the Fermi because it's minus, it's below the Fermi level. So we find that we have calculated for three values of the photon energy, 1.96, 2.70, and 3.54. We have increased these values and we calculate photocurrent. We find that when it's low, photon energy 1.96, the peak is very high. When photon energy increases to 3.54, peak is the lowest, almost flat. The reason is that because current is inversely proportional to the photon energy for that reason, as I've shown you in the formula given by Gao. Okay, Raffenberger. Here is the plot of, in figure 3.3 is the plot of photofield emission current as a function of applied electric field. So we find that it is decreasing almost exponentially in all these three values of photon energy, 1.96 electron volts, 2.70 electron volt, and 3.5 electron volt. We find that it is exponentially decreasing. And it should be also that because we have exponential term in the photofield current, as I've shown you already. Okay. Now, this is plot of matrix element as a function of photon current. Now, it is just coming from a high value and decreases. In one case, photofield emission, there is one oscillation here, whereas a matrix element, it is just going like this. Okay. It is not that much interesting to calculate MFI, okay, and as a function of photon energy, because this does not play much role in photofield emission current. This is the plot of transition probability omega for various values of the field we have calculated here. So it becomes almost a straight line when we have the highest field F4. F4 is 30 into 10 to the power 11 volts per meter. Okay. Now here we show the chronic penny Poisson model that has been used to calculate photofield emission current. But here, psi I, the initial wave function calculated is shown is here. This was done by Thapa and myself when I was doing my PhD work, and we published in Indian Journal of Pure and Applied Physics. And this formed the basic part in all my calculations of photo emission as well as photofield emission, because we have introduced a kind of potential acting on the electron. The electron is not able to move about freely. The final state wave function is we have picked up from the free electron model. Data is same as we have used for our free electron model. All are same. I show you the results here. Results is more or less same. The nature is same. Magnitude is slightly different. Okay, 3.6 shows you the calculation of the photofield emission as a location of electron with respect to Fermi level. Then in figure 3.7, we have again the same photofield emission current calculated as a function of applied field. It's I have done for two photon energy, 2.7 and 3.54. Same trends are shown as free electron model. Here also same trends are shown. Okay. Now here I show some experimental results. This is the experimental result which stated that it was published in 1984, which by Modines and Kleinet. They said that photofield emission current is when plotted as a function of this applied field, there are oscillations. That's what they have said. And here we show the results obtained by Lee and Shai. These are theoretical results for matrix element, means current as a function of photon energy. It is almost going like this straight line, or in straight line, it's more or less like exponential. That is what we have also obtained. And we have shown that there is no oscillations in our results just now. We have shown that there are no oscillations in the photofield emission current. Rather, it is decreasing exponentially. Here it is. In figure 3.7, it is decreasing exponentially. So this I'm omitting out. This is by transport Hamilton method. So now we come to the conclusion of our results. We have investigated the photofield emission current as a function of applied field as well as other parameters, which were shown in figure 3.3, 3.7, 4.1, 4.3. It is found that photofield emission exponentially decreases with the increase in the applied field. This is true as exponential term is involved in the formula for transition probability, d omega, in equation 3.1 and 4.c. Also, photofield emission current showed exponential variation with the applied high field. Matrix element is found to vary with the photon energy. Narrowing a surface which changes the variation of photofield emission. Means if we decrease the value of the surface with D measures the surface width. So it changes the variation of the photofield emission current. Then inclusion surface is essential in the calculation. Also, we have found that PFE shows opposite behavior in the case of narrow surface width than plotted as a function of applied field, as shown in figure 4.6, 4.7. So that was found in transport Hamilton case. Okay. So similar behavior as found by Lesjak in the case of tantalum and Hasdale. We have not shown for Hasdale done, but this Lesjak and Hasdale for tantalum and titanium. This included in their thesis. This is attributed to the contribution of d electron at electron stage, and this we confirm from the Dawes calculation that was done from these Bannister's calculations. Okay. Now there are so many drawbacks. So few are mentioned here. Same wave function used for bulk and surface region. Symmetric condition is required. So this is not true. Vector potential was derived from one-dimensional case. It should be correctly defined with aerodynamics for both surface and bulk structure. Vector potential was calculated without inclusion of the effect of applied high field. This is one of the big blunder that we have made. We have to include the value of this applied electric field in the calculation of the vector potential. Then only we can say that our result is 100% correct. Enhancement factor was not calculated. We have not calculated enhancement factor that we can, if we calculate the enhancement factor of current, then we can compare with the free electron model. Lattice constant are not optimized in both the case of tantalum and titanium. That was in the case of transport Hamiltonian. Wave functions are for simple case only, but tungsten is a D-band metal. The potential effects should be taken into consideration in both the cases. However, even with all the shortcomings, results obtained are comparable to other results. These are our publications, and these are our publication and conference presentations by Rosang Liana, mainly. Thank you for this. Thank you very much for your questions.
Thank you very much, sir, for your informative presentation. So if there is any question or any queries from the attendees, we shall be opening a few minutes to ask any question. Sir,
yes.
May I ask you for the sake of the attendees? So, yes. Since many of us are from from the applied science, and
Yes,
others are from the biological science as well.
Yes, I understand.
So they might not be understanding what will happen with those things. So can you please tell us the importance of this photo emission or the photoelectric field in our everyday life?
Yeah, I have already mentioned. Look, photo emission now. Now you all know that TVs are there, even in field eye microscopy is there, okay, which can probe the surface. So it is also microscopy, it is there. And then LCDs, TVs are there. Earlier we had CRT technology TV, is it not so? Now these all are, now research is going on, these all will be replaced, the screens will be, monitors will be replaced by the FDs, means field emission displays, okay, which will be sharper and brighter, very clear pictures will be there. For that reason, this technique has been also applied successfully in field ion microscopy, okay. Yeah, it's very difficult because one has to be, this is a technical talk. So
Yes,
I
sir,
understand that
absolutely.
from all fields are there. Okay.
Yes, sir, yes, sir. Any more questions from the audience?
Miss, I just like to mention that the explanation itself is very clear and clear cut. So as far as the presentation is concerned, there is no question. I think that is that is the problem with, you know, the other attendees also. And to have questions on the subject, we need to do some more reading. That's why.
Well, it's okay. I understand.
If there is no more questions, or if is there anything and more you want to say from your side, addition to the topic?
Yes, yes.
No?
It may be in addition to the topic, but first of all, I would like to say that I'm so happy to see Dr. Rebecca yourself as a faculty in the government Certificate College. It's my pride. Not only you, I'm sure there are so many students are there who are now teachers there, working as teachers, maybe in different fields in biology, whom I might have taught in +2 physics and all, okay? So what I would like to say is that take the responsibility as a teacher, okay? I have done my part for 40 years in Mizoram. Now this, everything is now on his shoulders. I'm sure wherever our students are there from PUC or from Mizoram University, they are all well trained, well groomed. I'm sure you will do very good for the science in 21st century, so that one day we will have our brighter and brighter students coming out and shining the name of Mizoram. So thank you so much once again to Dr. Rebecca first and all the organizing committee of this event, and to principal and all the faculty and the students of Government Certificate College. Wish you all the best. Thank you.
Thank you very much, sir. So now we have come to the end of this lively gathering. So I hope all the attendees are attending. All the attendees are having a very good time. So before we end up the meeting, I will like to express my gratitude to all the esteemed attendees of the webinar for their presence and contribution to make this webinar a grand success. Also, I would like to extend my gratitude to our esteemed resource person, Professor Thapa, who take his time from his busy schedule to grace this event. And lastly, not the least, thanks to our respected principal who took the heat in the preparation and success of this auspicious webinar. Thank you all and have a good time, everyone. Good night.
Good night. Thank you so much.